Good morning, everyone. So it's week number 2 for our lecture on type systems for correctness and security. Just a quick reminder, semester kind of officially, whatever that means, starts on the 20th. So this is all preparatory in some sense, but as we are at home and basically don't have anything else to do, why not start now? Either way, you can watch this recording whenever you like. As you've already seen, I've made it available on the university video portal as well, and linked it here in the Panda course. So everything should be available to you. If not, just let me know. And also what will be starting, so the thing that will be online later today is the first lab. For this you have 2 weeks, which basically means that if you start on the 20th, you have 1 week, and this is the exact amount of time that I have scheduled for this lab in the previous years. So there is basically no downside if you start next week with that. So don't worry. Good. Before we head into today's topic of actually starting to type a language, let me quickly give you some bigger picture excursions. So what are we dealing with in this course, and how does it fit into the landscape of general, or let's say general programming language design, compilation, execution of programs, and so on and so on. No? So what you typically have is in program compilation is that you have some kind of file that represents your program. So you have some file input output that reads your program either directly from your command line if you are, let's say, what's the right word? If you are adventurous and want to type in your program as you go, you can do that, or you have it in a file. Typically, you want to read it from a file. And so this is basically a stream of characters first. It's a stream of bytes, which is basically a stream of characters. And so you need some kind of little program that makes sense of these characters and tells you, okay, what are the tokens in this character stream? What is the thing that we want to recognize? This is called a lexer. This is basically just converting characters to so-called tokens. And these tokens, which is still a stream of things, some larger strings of characters that are tokenized. Let's say you want to recognize some keywords in Java that would be something like private or public and so on. So you don't like PRIV, you read public or private or whatever you have as a token. And these tokens are then put to a parser. And this parser then makes meaning out of this stream of tokens, as you see. And it converts these to so-called terms. Terms are then larger items, larger than tokens. They compress a few tokens together in so-called terms, something that are in a way syntactically sensible items that then a compiler can use. Something like a complete statement. Let's say I have a variable x, and then the tokens for this would be x, something like variable declarator, and an equals, which is kind of an operator, and then a constant 3, and then the semicolon. This would be kind of the tokens in this language. And a term would then be the complete assignment statement, saying, okay, x equals y semicolon is a complete assignment statement made out of these little tokens. That's what the parser basically does. And then this complete term is then given to the compiler, and the compiler then executes and makes machine code out of these terms. So executable code that then can run on your hardware. This is what the compiler does. And where does typing fit in? basically at the compiler level. So in typing, we are looking at complete terms. We are not regarded to implicit like single tokens. We're not interested in that, and we're not interested in character streams in general. It's not that we want to see different characters and provide different meanings with that. That's not what we're doing. We're looking at terms and making sense of these terms and trying to check if these terms are valid. Yeah, and in general, we do the same thing as a parser to some degree. So a parser checks if a program is syntactically correct, if it is fitting the language definition to some degree, and would be an acceptable program. So out of all the character and token streams in the world, the parser decides whether it is a valid program in that language or not. And later on, the compiler then has a few other checks, but let's say we implemented typing as part of the compiler, then the compiler then takes programs that are syntactically correct, the parser accepts it, and checks if they are also correct on a semantic level, if it is a well-typed program, a program that is adhering to typing rules. We're going to talk about this today a lot, but just have in mind, when you have like the complete set of all possible things that you can express with characters, the parser narrows this down to a smaller set of things, of programs that are syntactically valid, and the type system then narrows this down even smaller to programs that are also well typed. So you're basically funneling this down to something that is actually working in your language. That's the idea. So this is what happens when you look at things like compilation, when you run GCC or your Java compiler or whatnot. Java compiler is a different story, but let's say you have a C program, you want to compile it down. That's basically this picture. But what happens in our case? We don't compile, we don't build compilers in this course. What we do is called program interpretation. And this is basically the same steps as to when it comes to the file IO, the lexer, and the parser. So we also concerned with terms. What we don't compile them, we evaluate them directly. We can build a so-called interpreter that does so-called program evaluation, that takes the terms and basically executes them on the hardware. So what you do is you simulate basically the compilation step, in the sense that you do the same thing as the compiler, but you don't emit machine code, you just perform the operations yourself. So when you have this little example that we had before with x equals 3, you have something in your interpreter that is a variable store, so you know how to store variables, and you see, okay, we have a variable called x, and now we assign 3 to that. So you basically do that as part of your interpreter. So you have the program state basically in your interpreter, and you evaluate the program, and then you can provide output by these values. So the program evaluation doesn't output machine code, it outputs values. It just outputs what the program would output if you execute it. So that's the main difference. And we're building a lot of interpreters in this course because we need this. And interpreters are basically the execution of the semantic rules that we've seen before, the evaluation rules. That's why they are called that way. So when you see the first lab today, this will be basically the thing that you do. You evaluate a program step by step by taking the terms in this program that the parser has provided to you, and then you can decide on whether to accept this or not. But evaluation rules don't decide that. Evaluation rules just tell you what to do next, basically. There's this little evaluation relation that we learned last time, and this is what is to be done. Okay. Good. Parsing in general, that's the process that we call when we read a program from any input. We need to parse it. That means we have like a sequence of characters that streams into this parser, And what the output of the parser is a so-called expression tree, or what we call the abstract syntax tree. Yeah. So you have a representation of the program in a tree form, that combines all the tokens that were read before by the lexer into a meaningful way, so that the parser knows this is a valid program or not. And typically you don't code them by hand. Typically you generate them. You could, of course. You can code that by hand, and it has been done like in the past, but typically you don't do that anymore, because actually parser generators produce you much more and better parsers, much more efficient parsers than you could do by hand, actually. There's been a lot of research in a few decades now that actually provides you that. And the parsing that we're going to use in this course is in a special format called parsing expression grammar. And parsing expression grammar is basically a language for parser generation. So you have a programming language that basically gives you a parser as its output, and it's been like formalized. It's been around for some time in thought, in theory, but not like in a concrete formalized way. And the first formalized parsing expression grammar has been done by a person called Brian Ford in 2004, so it's rather recent. And it's been part of a master's thesis. So you can basically change the world on a master's thesis. That's the takeaway here. So don't be shy and don't be coy about your master's thesis. Your master's thesis can actually change the world, and this was one of the things that actually did. Of course, he later publicized this as a paper, but the first mentioning of parsing expression grammar was his 2004 master thesis. And of course, like from theory of programming, you know things like context-free grammars, so-called CFGs, but they can be ambiguous. So you can have multiple ways to decide if an expression matches that grammar or not. And in parsing expression grammar, that can happen because you have decision points and you have order. That's something you don't have in context-free grammars. That makes parsing expression grammars particularly easy to implement and decidable. So this, like, parsing in PEGs is a decidable problem and not an undecidable problem, such as context-free grammars can be. This is particularly important if you want to build something that you can prove that terminates, that you can prove that works, and so on. And CFGs are particularly hard with that. But so parsing expression grammars you can think of as almost exactly the same power as context-free grammars. There are a few minor caveats, but like in general you have almost the same power. But it cannot be ambiguous. It's easier to implement and it's much easier to read, to be honest. The thing is, if a like in converse, this means when you have a PEG parser that parses a string, there can only be one parse tree. There cannot be multiple parse trees that come from the same string. So it's a decidable, it's a deterministic problem. This is much easier to use. So we're using PEG grammar here, and like I like this style very much. So that's what I can say about this. If you want to read it, this is the Popple paper that came from his master thesis. Popple, it's called the Principles of Programming Language Conference. This is an ACM conference every year. This is kind of the most theoretic, but also one of the most prestigious programming language conferences. So if you make it there, you basically have you're basically accepted in the community on the theory level. I don't have a Popple paper. I would like to have at some point in my career. I never tried though. Good. That's kind of the first part of the lecture to get you into a bigger picture. Up until this point, do you have any questions that I can answer? Okay, does not seem to be the case. If so, please stop me in my further ramblings. Good. So next chapter for today, so this was kind of the prelude, but one of the two chapters that I want to present you today is we're going to take the things that we had in the last session about arithmetic expression, and we're going to build a type system that helps us prevent errors in typed arithmetic expressions. Yeah? So this is rather helpful to that sense. Good. Let me check. This all looks good. No, come on. Good. So first, let's start off with a quote. Luca Cordelli, you already know from the paper that I suggested last week. Peter Wagner is one of his many collaborators, and the interesting thing that they both mentioned in this 1985 publication is the road from untyped to typed universes has been followed many times in many different fields and largely for the same reasons. This is a hint. Typing, as we learn it in this course, is not only helpful for typing programs or implementing type checks for programs and so on. It has its foundations in mathematical logic and is actually a part of mathematics called category theory. So if you ever come across this, some of the things that we learn in this course will look very, very familiar. So category theory is a field of mathematics that basically is kind of an overarching thing over many fields of mathematics. So if you understand it, you can basically deduct from category theory to other things like typing and so on. It's basically the same thing, the same part of a metal as the other side of the same metal, to be honest. And we will also learn that typing has its foundations in mathematical logic and has also a lot of relations to that. So we can use typing to check problems from mathematical logic and vice versa. So we can transfer these things. This might be very interesting to those of you who are much more deeply into mathematical problems than the general computer science public, but it's nevertheless a very interesting excursion as well. And we will see that in the following a bit. So let's review that. What we had last time. We had talked about this language B, and if you recall, we had these terms in this language. There's basically like three terms in this language: true, false, and if T, then T, else T. So this is kind of the only expressions that we have in this language. Rather boring, but also pretty simple to understand. And we defined that values in this language are only true and false. So the only two things that can be kind of the end state of a program are called true and false. And then we have these evaluation rules that we talked about. These basically make up our interpreter. So the first two rules are pretty much simple. So if either it is true or false, take the first branch or take the second branch of the whole thing. So it's basically a rewrite rule, if you will. So all of these are. The EF rule is a little bit more complicated. It has a premise, and the premise is that T1 evaluates to T1 prime. So you can evaluate T1 to something. So T1 is not a value, and it evaluates down to something else. This is in this language true if T1 is in the form of an if statement, however nested that may be. But this is the only thing where you can actually evaluate something down. And then we exchange in this if, we rewrite again the T1 with T1 prime. That's in the lower part in the conclusion. So a pretty simple language, but a nice, interesting thing. But then let's say we extend this language with the other language n that we know, with natural numbers. Then the weird thing would be that we, like syntactically, also accept 0 here, because 0 is a valid term, and you can exchange it in t. This would also work. So let's have a look here. So this is the language n, which is based on b. The little dots give this away, that we take over everything that the term value definitions for b was. We take that over here, and we have these new terms called 0, successor of t, predecessor of t, and is 0 of t. And we can then see a different problem, because we will also accept true here, because true is also a valid term. It's a value and it's a valid term. And this means that we would have a problem, because we don't know what the successor of true basically is. We don't have an evaluation rule for that. We also don't know what the if 0 then true else false would be. We don't know that. We don't have that definition. So let's have a look at the evaluation rules of n again. And this is basically the same thing that we had last week. And as you can see, we don't have rules if successor true would be the expression that we want to evaluate. We wouldn't have a rule that works. And what would have then? We would have a stuck term, and this is our error condition. So we would have accepted an erroneous program in that language, and that's not good. So we defined last week that stuckness is our error condition. So when we would evaluate something like predecessor of false, we will be stuck. There are no rules to apply to this term. Let's have a look back. Predecessor of true, predecessor of false, we don't know that. There is no rule that works for that, because the ePred rule doesn't work, because t1 cannot be evaluated to some t1 prime. So this won't work. And the other rules, the pred 0 and the pred successor rule, also don't work. They are in the wrong form. So pred false would be a program in this language that is stuck. We cannot apply anything to that. And this is a runtime error that we consider right now. Stuck programs, we don't want stuck programs, basically. So what can we do now to not get stuck? To guarantee that terms will never get stuck? We could now define, of course, we could define evaluation rules for every possible value. So we could define the predecessor of true, the predecessor of false. But the problem is, once we extend the language again, this wouldn't scale. We would have to do this for every possible combination of values and terms in our language. So we would have like rules and rules and rules and rules and rules. And the moment when we extend this language even more, we have to think about all the rules and think about, like, could it get stuck? Would it get stuck? And so on and so on and so on. So you would have some way to distinguish between terms whose result would be a numeric value and results who would be a Boolean. And those of you with a little bit of programming experience already know, a numeric value is something else than a Boolean, and you shouldn't be able to mix those two in a language. And why is that the case? Because you type. So the answer to all of this is basically typing. And what we're going to do is we're going to introduce types to the terms. And because our language is easy, we just need two types. We need nat, which is basically representing natural numbers, and bool to classify Boolean terms. So we build a distinction about two distinct types of terms, if you will. So we have now two different classes or two different categories, in a sense, of terms. So this is different. and let's see how this actually works. So the way we're going to talk about it is called, when we say that the term T has type T, we mean that T obviously evaluates to a value of the appropriate form. Yeah? And this little notion called obvious, that's an interesting thing. We need to define what obviously means. So it doesn't sound very mathematic now, does it? So what does this mean? So with obviously, we actually mean statically. So statically means without any evaluation step. So we need to look at a term, and just by looking at the term, not looking at any evaluation rules, need to decide which type it is. And if you look at this term that is down here called predecessor, successor of 0, this is obviously a natural number that comes out, because successor of 0 is a natural number, predecessor of a natural number is a natural number, the successor of a natural number is a natural number, and the predecessor of a natural number is, as we already know, a natural number. Yeah? And this is basically the key insight to typing. Yeah? We need to be able to look at a term and all the subterms that it has, all the little things in the tree, and we need to decide down to the very leaves of that tree which type of this expression actually is. Yeah? As you can see, it's pretty easy for constants. So we know that 0 is a natural number. And we do actually know that the successor of a natural number is a natural number as well. Yeah? But we need to first look and decide that 0 is a natural number, of course. Yeah? And the way this works is typing rules. Yeah? But typing has a downside. Typing is very conservative in nature. If you have heard our other lecture called what's the long name? So the code analysis on large code bases that Eric Bodden does. You would know that static analysis is kind of an over approximation of this. So you would have more results than can actually be possible. Yeah? In typing, you have the opposite. You have, in a sense, an under approximation. So you would have programs that wouldn't get stuck, but your type system, in a way, rejects them either way, because it cannot statically decide if they evaluate down to a valid type or not. Yeah? Let's look at this example. So if true, then 0 as false. This would never get stuck. Yeah? This would never get stuck because it evaluates down to 0, and 0 is a natural number. This is fine. Yeah? But how do you know that without looking at the evaluation rules? Yeah? You couldn't, because both of like this example has two paths that it can result in. It's 0 or false. Yeah? And so 0 or false are not of the same type, and false are not of the same type, so the whole expression cannot be typed. Let's step back to the typing rules, to the syntax rules. Sorry. So predecessor of successor of T would be predecessor T, yeah, and in T you can insert successor of T. So this would be a valid program, but you have to do something with the T in your expression. Yeah? Good. Coming back. So typing is kind of conservative. Yeah. So even though this program would never get stuck, we would disregard it. It wouldn't be possible to type this thing. Yeah? At least with the simple notions of typing that we will be concerned in the first part of the course. There would be some ways to make that actually work in some sense, and to be a little bit more precise here. But in general, this would not be acceptable. So typing is conservative. Typing prevents errors, but also prevents some programs that will never get stuck from actually working. Yeah, it will reject them. So, excuse me. First thing that I want to introduce today is the so-called typing relation. And this is something very, very foundational to the course, and to typing in general. So the thing that we say is that there is a term T that can be typed as this large T. So we assign each term a type. This is a relation just as any other relation that you learned in the previous lecture. So the way to read this is this term has this type. So this little colon in the middle basically tells you this is a typing relation. And the way to read it is this term has this type. Small t has the type large T in this sense. And this is the way that typing rules are made up. So the first thing that we need, that's why it's in blue, is we need new syntactic forms. We need new ways to express these types in the source program if we would like to. These types become part of the syntax of the language. So bool and nut are now valid tokens in that language. And the first two rules that are just below this blue box are called t-true and t-false. So the t basically tells you it's a typing rule. Well, it's convention, but pretty neat. And these two rules give you an insight about how to type values. So these two rules basically give you that true is a Boolean and false is a Boolean. So they ground you basically. The same is true for on the right side for this T0 rule. So they tell you, okay, 0 is a natural number. And now these are the more interesting rules. That's the first the TF rule, which we're going to do in a second. But let's first look at this T successor, this T suc rule. And there you have an interesting relationship. So the premise for that to be valid is that T1 is a natural number. And if T1 is a natural number, then the successor of that natural number is also a natural number. So this preserves basically the type in this operation. Same is true for this T-pred rule. And then there's a little bit of a difference because is 0 is kind of a Boolean predicate. It tells you, is it 0 or is it not 0? So given that T1 is a natural number, is 0 of T1 would be not natural number, but Boolean, of course. And this is pretty interesting. And now you have a notion of typing in these expressions. This is really, really neat. The other rule that you see in here is the so-called TIF rule. And the TIF rule is a little bit more complex than the others. The first premise that you see on top here is that you cannot say if 0 or if 1. You need to be if true or if false, or something that results to a Boolean. So another if, or you could use is 0, interestingly here. Then the other premises look a little bit strange because they don't actually give you the type. They just tell you, okay, T2 needs to be of large T and T3 also needs to be of large T. And then in the conclusion, you see that, and then in the conclusion, you see if T1, then T2, else T3 is also of type T. And this is a very interesting thing because it binds these rules together. It binds these variables together. So the result of the if statement will be the type of T2 and T3, but the type of T2 and T3 need to be the same type. And this is the very important insight here. Okay, so we do have a question on the slide. So can we have one more rule for tsuc called tsuc bool that says if T1 is bool, the successor of T1 is bool? Yes, we could have, but wouldn't make any sense. So how would you say, well, what is the successor of a Boolean? You can define this rule, but then it wouldn't fit to the evaluation rules again. The relation between typing and evaluation, so we actually see that typing prevents us these errors, we will see in a second. Bear with me with that. But of course you can define this rule, yeah. But then again, your type system wouldn't prevent you from errors, yeah, because there is no evaluation rule for a successor of a Boolean value. Unless you define one. If you define one, then you're fine again. Then you don't have a stuck program anymore. But other than that, you would have that. Good. Hope that answered your question. But bear with me for a moment, and it will become a little bit more clearer when we see that the relation between typing and evaluation. So typing relations for arithmetic expression. Okay, good. So if you put it in a formal sense, and we try to do this in this lecture, that means that this typing relation for arithmetic expressions is the smallest binary relation, two things together in a relation between terms and types. So terms on the left side, terms on the left side, types on the right side, satisfying all instances of the rules seen on the previous slides. So the same thing as we did for the evaluation relation, we can define such a typing relation as the smallest binary relation between terms and types, satisfying all instances of the rules seen on the previous slide. So we say that a term T is typable or well typed. This is also an expression that you see very often in literature. If there is some large T such that the term is in a relation with that type. T is typed as large T. Another thing that you can do, this is a trick later on for any kind of proof that we're going to do, is the inversion of the typing relation. So you had these rules, and these rules form a relation. And now you can invert this relation and then have rules that help you with that. So when you invert these typing rules, we learn the following. So if we have an expression that is called true types as R, then R must be a Boolean. There is no other way. And if we have an expression called false types to R, then R types to Boolean. Same thing. Same thing goes for natural numbers. This is here, this clause number 4. And the same thing is true for all of the other relations that we just inverted. So it's basically the inversion of the conclusion and the premise a bit. So you can use this inside pretty much in every proof that you need. And one of the proofs that we're going to do a lot without even calling it a proof is actually type checking. Type checking is the way to see, is a term in relation with a particular type, or can we check, can we find a type where this is satisfied. Let's do this for a moment. So this is called typing derivation or type checking. And the interesting thing is that it naturally forms a tree. You will see this in a minute. I cannot yet draw on my slides. I will prepare that for the next week, hopefully. But then it will get a little bit sort of. For now, we have to use our imagination a little bit. So let's say we have this term down there called if is 0, 0, then 0 as predecessor of 0 is a natural number. Let's say we want to show that this is true. That this is actually in like the left side, this term is actually in relation with the type. Then what we do is we look at all the typing rules that we have and try to apply them backwards. So we look at something where the conclusion looks like the thing that we're going to type. You know? And there's the T-if rule. And then we can retroactively take all of the premises from the T-if rule and build them up and try to split the term up that we just saw. So the first thing that we split out is, of course, the condition. You know? And the condition is 0 true is a Boolean. And this has the form of the T is 0 rule. And the premise of the T is 0 rule is that 0 is a natural number. And this immediately follows from the T0 rule. Yeah, so we build up one branch of the tree upwards. It's a computer science. It's the inverse of a computer science tree. It's actually growing upwards. Is giving us something that is an axiom, something without a premise. And then we've shown this path basically on the tree. Going to do the same thing for the other branches as well. Okay, the T2 branch of this is a 0 is a natural number, and this is the T0 rule. Yeah, again, this forms pretty nicely. And then we have predecessor of 0 is a natural number, because we already learned that the type of the for this thing to type, yeah, we need that the branches are natural numbers. We learned that from the conclusion of the T-if rule. The nut is already given there, so it immediately follows that the branches for T2 and T3 must also be natural numbers. Yeah, so this is the thing that we're trying to show here. For the middle thing, for 0, this is quite trivial, but predecessor of 0, do we have a rule for that? Yes, the T-pred rule, and the T-pred rule has the premise that 0 must be a natural number, which is then apart from T0. This is basically what type checking is all about. This is what a type checker does each and every day, each and every minute and second. Yeah, it tries to apply all the typing rules kind of inversely to the thing you're trying to show. Yeah? In this case, we had kind of the outcome fixed, so we already assumed that the result of this would be of type nut. Yeah, but we can also leave this open as a variable and check if we have some contradictions in this tree that doesn't allow us to make this assumption. You know? So typing derivation usually works as a tree of instances of typing rules, and this is a very important insight because this basically is the implementation pattern for a type checker. So in other words, we can say that statements, something in the programming language, are formal assertion about the typing of a program. Yeah. Interesting. We use vocabulary for mathematical logic to talk about programs. Typing rules are implications between these statements, and derivations are deductions on typing rules. So this is the first kind of insight on a parallel to mathematical logic here. So we use mathematical logic or logic deduction basically as a way to talk about programs and to help us figure out if a program is acceptable, valid or not. Good. A few definitions what we can do. So one of the properties of this type system, this particular type system right now, is so-called uniqueness of types. And you have that when each term has at most one type. So we can assign one type to each term and not multiple ones. Yeah, that's called uniqueness. And that is, if T is typable, then its type is unique. Yeah? There is just one derivation of this typing built from the inference rules. There is no ambiguity here. This is a property which we will drop in one of the upcoming lectures. But right now we have uniqueness of types. No? That's very important because it will help us a little bit because we know when we're done. We don't have to consider that there are maybe alternative solutions to the problem. When we have shown that a type system actually has this uniqueness property, we can we can spare ourselves a lot of work. No? Good. So how do proofs of properties of typing relations work? So now we learned uniqueness. How do we prove that this is actually true for our typing relation? And we already have seen in the last lecture that we can check for properties on evaluation relations. Yeah, the things with size and depth that we did. Yeah? And for this, we did induction proofs on evaluation derivations. Yeah? We get to the evaluation derivations that looked at the different cases and looked if this property holds for all of them, and did an induction proof. No? Same thing we can do for properties on typing relations. Yeah? What we just do here is induction on derivation trees. The same property as well. We have a tree structure, and we can do case by case logic and look at the induction of this. The first thing that we want to do this is a property called type safety. And type safety is, besides uniqueness, one of the most basic properties a type system can have. And this is something that we want to achieve. It's also called soundness. You also see that a lot of times in literature, soundness or type soundness, that's basically the same thing as type safety. And this is type safety is the basic property because it prevents us from erroneous programs. It prevents us from things that will get stuck in our definitions. This is usually a property you want to have in a type system. And you want to know that like well-typed programs that the type checker accepts will not get stuck. This is our ultimate goal. And type safety is made up out of two other properties that compose together as type safety. And one is progress and one is preservation. Oh yeah, I did some animation for that. I forgot, but here it is. So progress and preservation. So let's look at progress first. And this is the formalization of progress. Suppose T is a well-typed term. So that you have the assumption that T is already a well-typed term, a well-typed program. So that T is in a relation to large T in the typing relation for some T. You don't want to know which type, you just say, okay, it's well-typed, it has a type, it can be typed. What this means, if you make these assumptions, is that either T is a value, or else there is some T prime that T evaluates to. That's why the property is called progress. You can make progress in the evaluation rules. And you can prove this progress property over and in our type system. So this is the application outside of the box. This is the application to our type system then. You can prove this by induction on the derivation of T. And the first thing you can do this is for the rules that actually describe values. So this is the T true, T false, and T zero rules. You remember them, this was just like value types to trivial type. So true and false are both Boolean and zero is a natural number. And this is really immediate. You don't just need to look at it because like T in this case is a value. So the first part of the either or is actually true. So you have progress for these rules. And now you have some next cases which I will present you in the following slides. So for the values that was pretty trivial, but we do have these other rules that we need to go through. So we do this now case by case. Same thing as we did for evaluation rules, but now for typing rules. So let's look at what we have if the case is a TF. If this is kind of the rule that we currently apply, then our term is in this form. It can only be in this form, otherwise it wouldn't be applicable to this rule. So T is if T1, then T2, else T3. So the most general form of an if. What we also know from T-if, because otherwise we wouldn't have this case, is that T1 must be of type Boolean and T2 and T3 must have the same case. So how do we describe progress here? How do we now say that T actually evaluates down to a T prime? Now we need the evaluation rules again. So if we then look at the induction hypothesis, either T1 is a value or else there is some T1 prime such that T evaluates to T1 prime. So this is the induction hypothesis which you can apply to the subterms. This is pretty easy. So if T1 is a value, then it must be either true or false because it's a Boolean. It's the only two values that can be Boolean. We already know that from the previous proof that we did. And in which case, either if true or if false applies to T. So if T1 is a value, then this trivially works. So we have proven this in the case that T1 is a value. So what happens if T1 is not a value? Well, then we can also progress T, because T1 evaluates to T1 prime. We assume it's well typed. Remember, then we can apply the if rule, and then T evaluates to if T1 prime, then T2 else T3. You see? Now we went to all the cases that may happen for an if, and we've now shown progress for the T-if case. Okay. What else is there? Okay, the T-successor case, of course. If this is the case, we know that T is of the form successor of T1, and we know that T1 is prime. And then we can again use the induction hypothesis that either T1 is a value, or else there must be some T1 prime that T1 evaluates to. So again, two subcases. T1 is a value, then this must be a numeric value because T already was well typed. And if this is the case, if T1 is a numeric value, also is T. Because then we have shown that the T successor rule applies. This is nice. So the other case is that T1 evaluates to some T1 prime, and then we can use the E successor rule because successor of T1 evaluates to successor of T1 prime. T1 prime. And then we have shown all the cases for T-suck again. For T-pred, basically that's the same thing, but we have a special case here if this case is 0, so it can be either 0 or successor of numeric value. We have to be a little bit careful about that, but in other case this proof works entirely the same. So the other thing that we have left is the case is 0, and here the term has the is 0 of T1, and T1 is a natural number, and all of this works similar. Other than like the result is a Boolean, but in general the proof schema is absolutely the same. As you can see, a mathematical proof in that sense is not something to be feared. It actually just works by going through all the cases and checking that you have checked all the cases. Nothing more than that. And you can use the induction hypothesis, which is very convenient, and you can use the inversion of the typing rules, which is also very convenient, and then come to a conclusion. Good. So this was progress, and I already said that this is only one of the two properties of type safety. The other one is preservation. And preservation means that if you have a term that is well typed, T is of type large T, and this term progresses, so there is a T prime, then this T prime is also of type T. So this means whenever you evaluate something, a term, then the term must be preserved. This is interesting because like we have like one operator, the is0 operator, that changes in between subterms and terms. Yeah, that's gotta have this in mind. Yeah, good. So is this actually true for our type system? Let's find out by proof by induction on the derivations of T is of type large T. Yeah. And as induction goes, that at each step of the induction, we assume that the desired property, preservation, holds for all subderivations. Yeah, that means that if S is of type large S and S evaluates to S prime, then S prime is also of S. Whenever S is of type S is proved by a subderivations of the present one. Yeah, so this is the mathematical sense to say that, to say the same. Yeah? So as it's an induction proof, we assume that the desired property holds for all subderivations. Yeah, and now we can do a case-by-case analysis on the final rule of the derivations. Yeah. Again, as you can see, this gets a little bit repetitive. I'm only going to show you a part of that. The other ones are quite similar. If you want, you can do them on paper, but again, it's very boring because it's basically the same thing. You need to understand the mechanics of these things, not to like repeat yourself. Yeah? Okay, let's look at the most trivial cases. So let's say we have the case T true, then it must be the case that T is in the form of true, yeah, and large T, so the type of T, must be a Boolean. Yeah? So if the last rule in the derivation, reigns, you have a tree, and the most bottom part is T true. So not a very fancy tree, just basically one single node. Yeah? Then we know from the form of this rule that T must be a constant true and T must be bool. But then T is a value, so it cannot be the case that T evaluates to T prime for any T prime, because values don't evaluate anymore. And the requirements of the theorem are so-called vacuously satisfied. So the theorem, let's go back here. The theorem is the one in the box. Requires that we have something that evaluates down to another T prime. This is not the case for values, so we do not need to show this for values, because values don't evaluate, so they cannot preserve, or they preserve naturally, whichever you like. And this is what we call vacuously satisfied. So the theorem is true for that case because it just simply does not apply to that. It simply does not hit. More interesting. This is the case for the T-if. This is a term that is trivially not a value, because it's called if T1, then T2, else T3. And from the T-if rule, we know that T1 must be a Boolean and T2 and T3 must be of the same type. So again, we look at the last rule in the derivations, and if T-if is the last rule in derivations, then we know from the form of this rule that that T must have this form that we just mentioned for some T1, T2, and T3. T1, T2, and T3 are not very important here. We must also have subderivations with conclusions T1 bool, T2 T, and T2 T3 large T. And now we're going, when we look at the evaluation rules of N, with if on the left hand side, we find that there are three rules by which we can say T is T prime, which can be derived. So we have this E-if rule, the E-if false, and the E-if rule. Only these three cases exist. So let's look at each of them separately, but like not look at E false because this is similar to E true. Oh, good. So subcase for this would be E if true. And if this is the case, this is kind of the case we're looking at, then we already know that T1 must be true. And T prime is T2. Yes, this is what immediately follows from the E if rule because it evaluates to T2. So if T evaluates to T prime is derived using E if true, then the form of this rule, we can see that T1 must be true, and the resulting term T prime is the second sub-expression T2. This means we are finished, since we know the assumptions of the T if case that T2 is of type T, which is all that we need. The whole term is of type T, and the subterm is also of type T. This is what we needed, and this pretty much works. By the way, here now I come back to the T-suck rule, where this question was asked in a second. But let's look at the other subcase. So the T-false case basically works the same. So the interesting case is if T1 is actually in the form of an if. It is actually in something that can be evaluated down. So T1 evaluates to T1 prime, then T prime is if T1 prime, then else T2 else T3. This is the if rule basically. What we can now use is the assumptions of the T if case. So we have a subderivation of the original typing derivation whose conclusion is T1 bool. So we know that the type of T1 must be bool, and also because we're in induction land, T1 prime also must preserve bool. We can use now the induction hypothesis on the subderivation, obtaining that T1 prime is also of type bool. And when we combine this now with the facts from the assumptions of the T if case that T2 and T3 are both of the same type, we can now apply the T if rule to conclude that if T1 prime, then T2 else T3 is of type T. That means that T prime, so the evaluation of this thing, is of type T. So we now preserve the type for the T if case. If you had a little trouble understanding this, draw this on a piece of paper and draw some lines between these rules, and then it will become immediately clear. Maybe I should do this on the slides at some point. Good. Preservation, again, we have more cases. We have the T0 case, basically the same as the T2 case. So T0 means that T is 0, so is a value, and this cannot happen. We don't need to show preservation for values because values just preserve. Values are values. So here comes now your question on the T-suck rule. If we would have like a second rule for T-suck, then we couldn't do this. Just imagine you do this for Boolean. The problem is now in this preservation proof, we need to show that that T is of this case T-suck T1, where T1 is a natural number and the whole type of the thing is a natural number again. You could like formulate this for the other rule that was asked in the chat, meaning that you had a T-suck bool rule, where the premise is T1 is bool and the successor of T1 is also Boolean. The problem is that you now in this proof use the E-suck rule, and you don't have a definition to do this for Boolean values. Let's look at how this works for natural numbers. So by inspecting the evaluation rules of n, we see that there is just one rule, the E-suck rule, that can be used to derive T evaluates to T prime. And this, the form of the rule tells us that there is T1 to T1 prime, which we also know is a natural number, and we can use the induction hypothesis to obtain that T1 prime is a natural number, from which we can obtain that successor of T1 is a natural number. Yeah, so that is T1 is of type large T by applying the rule T-suck. Yeah. This wouldn't work if we have Boolean, because we couldn't ground this. We could do the assumption that this goes down to Boolean values, because we don't have actual Boolean values for that. Yeah. Good. This is, I think, one of the most interesting cases in preservation, because we have an argument to this operation, which is a natural number, and the result is a Boolean. Yeah. This comes a little bit strange, because all the other operations either worked on natural numbers and produced natural numbers, or worked on Booleans and produced Booleans. For this is not the case. Yeah? So let's look how this here works. And the interesting thing here is that by inspecting the evaluation rules of n, we see that there are three rules which can be used to derive t evaluates to t1 prime. Yeah? There are two rules, the e is 0, 0 and the e is 0 suck, which evaluate to a Boolean value which preserves t. The interesting thing is here now, the whole term is 0 t1 is typed as Boolean. Yeah? So the evaluation of that is a Boolean. It's either true or false. Yeah? You see, it doesn't matter what the type of the argument actually is, as long as it is fitting the type derivation. Yeah. Let's look at the remaining rule. This is e is 0, and the form of this rule tells us that t1 evaluates to t1 prime, which by the induction hypothesis preserves t. So the natural number inside always preserves. Either way you turn it, you preserve it. Yeah. And this is basically how this works. Yeah, this is how you prove preservation for t is 0. So don't be fooled by the types of the arguments. You got to look at the type of the complete term and what it evaluates down to. Yeah. And by the assumption that you already did this for all the subderivations, this becomes very, very easy to do. Yeah. Good. So this is typing in a sense. So what we did is we checked types for different terms. Yeah, we made up rules for that, and we showed progress and preservation for these. We didn't show uniqueness. That's part of the exercise, by the way. But same goes here. It's the same proof pattern. It's the same proof pattern throughout the entire course. So you don't learn a new pattern there, but you apply this pattern again and again. All of this basically relates to chapter 8 in the book. Before we start with the next part of the lecture, I'd like to take a little bit more time for your questions on that part. So if you have questions, now would be a good time to tell them. Also, for those people watching offline, of course, you can also all the time post them in Panda. Try to answer them as soon as I can. If you give me some reference to the slide numbers, this makes things a little bit more easier, actually. Okay, so someone is starting a question. So the question was for preservation and summary. Preservation derives one rule and then preserve that rule to derive other rules. That's not how I would put it. Let me just quickly go back to the definition. So preservation is a property that basically tells you if a term can be typed as this large T. So term is the small t, and it can be typed as this large T. And we have an evaluation. It's also in an evaluation relation with T prime. So that says we can evaluate T down to T prime. Then it does mean that T prime is also of this type T. This is what preservation gives you. So however you evaluate this thing, it must always preserve its type. That's the important part here. What we now did is we have proven this property. We have shown on our type system, on our typing rules, that this property holds. And if both of these properties, preservation and progress, if both of these properties hold, we have a type safe type system, which basically tells us we cannot produce any programs that satisfy these rules that will go wrong. That's the general goal that we have. What we now did in this proof, is then we looked at subderivations and said we assume that for all subderivations this holds, and then we gone through case by case if this is if this preservation property actually holds for a type system. So that was basically the proof of that. But the property itself just says if we can type a term and we can evaluate that term to some other term, then this other term must be of the same type. Sure, for is0. Yes. Okay. There we go. Okay. So the question was if we can go over the preservation property for is0 a little bit again. No? Okay, good. So good that I could answer the first question. Good. Here the question is how does it work for the is0 case? So we are in the proof and we are in the case that we want to show this for the t is0 rule. So t must be of this form is0 t1. We know that t1 is a natural number. And t must be bool. So whatever, when we find something, when we find a t prime that this is0 evaluates to, then this t prime must also be of this case bool. It must also be of the type bool, sorry. And how do we find things where t evaluates to? Well, we need to have evaluation rules. And we find 3 rules that can be used to derive that t evaluates to t prime. And the first 2 rules for this to be true is the e is 0, 0 and the e is 0 suck. And they both evaluate to a Boolean value, because is0, 0 evaluates to true and is0 suck evaluates to false. Both are Boolean values, so that preserves t. So we've shown that. Check mark. Okay, so there's one remaining rule, and this is the e is 0 rule. And the form of this rule tells us that we have that t prime can be evaluated down to t1 prime. And then we can use the induction hypothesis to say, okay, for this t1 to t1 prime, this also must preserve t. In this case, this type of t1 is natural number. We also know this is this net up there. Already know that. And then sooner or later we will have one of the other cases. The e is 0, 0, the e is 0 suck case, which always reduces down to a Boolean value. And then we've shown, okay, we've shown all 3 cases where we can derive t to t prime, and then we've shown that this is actually true. So this is how the proof for is0 works. Okay. More questions before we move on? Aha, that's an interesting question. So how does progress ensure that there is no cyclic derivation? We can guarantee that t eventually evaluates to a value, or is this covered by another property? Interesting question. Currently we cannot do that. Or do we? Progress. Let's go back again. So the question was like, how can we ensure that there's no cyclic derivation if we don't have like evaluation rules that like produce cycles? Currently we can't. This is like non-termination is currently not our error condition. We want to preserve, like we want to check for stuckness. That's an interesting case. We will actually come to that in a later sense. But let's have a look at progress. So progress just tells us, suppose T is a well-typed term. Yeah, so we can say that T is of type big T. Yeah, then either T is a value or else there is some T prime that this thing evaluates down to. So this property just says, okay, we can do progress. This is in no sense some way of some kind of termination criteria. We don't know that yet. We just know that like in a single step evaluation we can come to a next step. We don't know anything about the step. The step could be the same as the previous one, but we do make progress. So currently termination is not encoded in our type system at all. We just assume that it is terminating, but we don't know that. We haven't formalized that yet. We just say that it is either a value or there is something where we can evaluate it too. We don't know that T prime might be a form that just evaluates down to T again. But we will come to termination a little bit later, and you will see it's tricky. Good. More questions? So the question is, if it does not evaluate to T, then isn't it stuck? What does evaluate to T? If it does not evaluate to T, then isn't it stuckness? No. We want to make progress. So some T prime that might be different. But for Paul's question, no. Just let me quickly backtrack on that. No, it doesn't need to evaluate to T. It needs to evaluate to some T prime. But there is no there is progress that just doesn't like force that on you. Hopefully all of our derivations will eventually evaluate down to a value. But currently we have not shown anything about termination. It's interesting that as this soon in the course you're already thinking about termination, but we'll come to that. No, stuck is only when we don't have any evaluation, when it is not a value, and when we cannot find a T prime. When we can find a T prime, even though it's cyclic, this is fine right now in our definition. Okay, let's move on, otherwise we don't have the time anymore. Good. So in the last hour, I'm going to talk about a different way to describe programming languages called the so-called Lambda calculus. And the Lambda calculus is more like a unified framework for programming language design and proving properties and showing things. It's a very basic thing in some universities. You do have this in your bachelor programs, but I highly doubt that you had it in Paderborn. So I will teach it from the very beginning. I also add a video that from another professor that also like sums up the explanation of this quite nicely in my sense. So you have like multiple views on this as well. Hopefully non-conflicting. To my sense, it was not non-conflicting, but let's see. So what is the untyped lambda calculus? So we're not typing at the moment. We're doing this next week. And so what is the lambda calculus? So the so-called untyped or pure lambda calculus is kind of a computational substrate, if you will. So this is kind of the most basic, most simple thing that you can define computation or programming in general. And this makes it extremely helpful if you want to define type systems, because whatever holds in the lambda calculus can be transformed to any other programming language, because it's so pure and so basic. You can map it to any more sophisticated programming languages in the entire world. And understanding the lambda calculus is not only key to this course, but also to understanding type systems, as well as other interesting research areas. You had if you heard Eric Bodden's lecture on Dicker, you had a small piece of the lambda calculus at some points in there. You almost wouldn't recognize it, but like it's in there, and it feels very natural to actually work with that. You will see, but there are some tricks that we need here. Yeah? And the lambda calculus was basically invented by an American mathematician called Alonzo Church. You would have, like in one of your theory courses, heard of the Turing-Church conjecture at some point, and this was the person behind that. He didn't invent this for programming at all, because like when it was done, like programming was still in its infancy. So the idea was that you had like a system of logic, a system of mathematical logic. But even then, like in the first publication, he wrote this very famous sentence: "There may indeed be other applications of the system than its use as a logic." This is what we basically did as computer scientists. We took this mathematician's work and just applied it to our case. And it works really, really well, as you can see in a minute. And then there was a British computer scientist by the name of Peter Landon that basically made that transition. Yeah. He made that observation that like complex programming languages can be understood by formulating it as a tiny core calculus for this language essential mechanisms. So programming languages like developed independently, yeah, and then someone looked back at the mathematical literature and said like, okay, we reinvented the wheel. This has been done already, and like they formed like the connections and all the things that basically came out of that. Yeah, and by Peter Landon, this means that like he invented that kind of a collection of so-called derived forms, translate advanced features into the core. We will actually do the same as Peter Landon did. So we will first learn kind of the core part of the lambda calculus, and then have all kinds of derived forms that translate back to that. If you are much more proficient in Python and in YAML and so on, maybe Haskell and Scheme, this is a little bit more exotic, but maybe you know that too. There is the so-called offside rule to delimit declarations. That is a Peter Landon invention, basically. Yeah. Also in make files you have that. There is out there other calculi. The lambda calculus is not only the only thing in the world. There is this notion of the pi calculus by Milner. Sorry for the typo. It's actually Robin Milner. Milner, Poirot, and Walker. This describes the semantics of message-based concurrent languages. So something, languages like Erlang, for instance, that are based on messages and based on concurrency. Those are much better described with pi calculus, because this has some forms of things that like happen side by side and so on. We don't have that in Lambda calculus, as you can see. But if you're looking for like concurrent programs, the pi calculus is a much better fit. And then there was this book by Abadi and Cardelli. Luca Cardelli, we already know, but Martin Abadi is the other one, called the object calculus. And this was a way to describe object-oriented languages in its own calculus, rather than applying the Lambda calculus for that. As this is a little bit more complex, in this course we will be doing the application of the Lambda calculus to object-oriented language, and don't consider the object calculus right now. But if you understand the one, then it's easier to understand the others, so vice versa. It's already helpful. And the theory of objects is not that used much anymore. The pi calculus is. The theory of objects is like seldom used. You mostly find things based on the Lambda calculus. Current research. So the Lambda calculus pretty much boils down to two basic operations. It's not much more. It's two basic things. And the one thing is called a function definition. You should be pretty much aware with those. So you define a function. So this is the first basic operation in the Lambda calculus. And the second thing is function application. And just by these two, you can basically express all computations out there. You don't need much more. You need function definition, you need function application. And that's the Lambda calculus. It's not much more. And the syntax of the language is as follows. So you can use things as variables. This is this x. And then you have the first part, so this lambda x dot t is a function definition. And what it means is I define a function, this is what the lambda stands for, with an input parameter called x. And this goes into a body of t. So t is kind of another term that describes what happens in that function. And x is an input parameter that can be used inside of this function. As you can see, only one parameter. We will come to that. And the third line here in the syntax definition is function application. So that means that you can, it's a little bit hard to read because both symbols are the same. And it means the first t is the function and the second t is the parameter. So you apply function t, the first one, sorry for that, and to the second one, which is the parameter. It will come very naturally when we look at the evaluation rules of that language. But this is the only syntax that you need in the Lambda calculus. As you can see, it's pretty small, simple, and rather beautiful. So not much in there, not much fuss. So, as I said, this is a variable. This is a so-called function definition or so-called abstraction. And this is a function application or short application. So you basically have these two concepts and a variable, nothing more. Abstraction, application, and variables. Not much more in the syntax. For this, we need to look a little bit at concrete versus abstract syntax. So the concrete syntax of a language, and this is again just basic computation. This is not the Lambda calculus. You can do two things. You have these concrete syntax, 1 + 2 × 3, which can either be a parse tree like that. So you have on the top a plus node that has on the left side a 1, and on the right side this times operator, and then on the left side the 2 and on the right side the 2. But you can also parse this into this. And by your sense of computation, this would feel wrong, because operator precedence is not considered here. But this is kind of the same thing here. The concrete syntax on the top of this expression does not give you operator precedence, so you have to you have to encode it in some sense. What operator takes precedence, but both trees on the bottom would first be okay if there is no operator precedence. Of course, the thing on the right you wouldn't consider. You want to do the thing on the left. And for the lambda calculus, it's basically the same. So you have these very small expressions in parentheses s and t and then u. What does this mean? This means that s is applied to t first, and the result of that, which is a function hopefully, is then applied to u. So the concrete syntax on the left side, stu, is translated into concrete syntax on the right side. You have this implicit node called apply that comes from the operation of function application. So the concrete syntax and the abstract syntax are a little bit different in the lambda calculus than you've seen before. But it's just a system to get into your head. Nothing much more. So how you read it is apply s to t and then apply the result to u. That's how lambda calculus works. It's all function definition and function application. In this case, it's just function application. We assume that s and the result of the application of s to t are functions. We don't say anything about t and u here, but what else is there than functions? So a little bit more complex, if we look at the abstract syntax tree of a lambda expression, is this. So the top node is basically a definition of a function that takes x as a parameter, and then you have in parentheses these function definition on y, and then you have the body of the function definition after this dot. And what happens there is x is applied to y, and the result is then applied to x again. And this is the function body of this inner function that takes a y. And the whole thing, the function definition for y, is then again in the function body for this function that has this parameter x. So in contrast to other programming languages where you give a function a name, you don't have a named function here. You only have a function definition that takes a parameter. You don't name those. Good. Of course, we need to look a little bit at scoping of variables. So we define a few variables here. We define input parameters for functions. So we need to be a little bit aware of scoping. So you have this function definition called lambda x dot t. And this means that x is bound in t. So whenever x is used in t, it is bound to the value that is provided as an input to this function. We call the thing on the left side of the dot the so-called binder. This, lambda x, binds x in t. And we call t the so-called scope of the variable. Well, this is pretty much important because this is interesting. We will see a few examples later on how scoping works. But let's look at lambda expressions in other languages. So other languages have started to include lambda expressions as a means to easily put in things. And in Java, this looks a little bit like this. You have an argument list, so you can have multiple arguments. You have a body. So in this lambda here that says sayable s1 equals, and then in parentheses name, you have a lambda expression. So you define a lambda expression you might do a function definition, yeah, um, and you bind these this function definition called s1 to this lambda that you just define, which takes an argument list, in this case name, and then it has a body, which is basically here in these curly brackets, a return hello plus name, and so on. Yeah. At this point, you didn't execute the function; you just defined it. Yeah. And later on in this system out print line, you take this s1, you execute say, which is kind of the interface for all of this. Yeah. You could do it easier. It's just for illustration. And say put in name, bind name to class. This is basically the same thing as in the theory. You bind a concrete argument into this argument list here. In C#, this looks a little bit like this. So you have anonymous function signature, and then this little arrow with the equals, and saying which results to anonymous function. So this is this line called del mydel equals, and this is lambda expressions in C can be C# can be a little bit easier, but in general they're modeled as delegates. Yeah. And the signature of the function is basically just the x that's on the left side, and then the function definition, the anonymous function, this is kind of the body of the function, is x times x. Yeah, so just the square of x. And then you can execute this function in the next thing by just using the name of it, mydel, and applying it to this value 5. So 5 is then bound to x, and x is exchanged by 5 in the function body. No? That's how it works. As anything in C++, it's a little bit more complex syntactic wise. And this is how it works there. So you have something like a struct here, and inside of this struct you have a lambda expression, which gives you this little neat definition with the equals in this brackets and so on. But then again, you have an integer parameter which is bound then, bound, and then you have like the return operator and this times to return of the body. So this is a little bit strange for syntactic wise, but this is how C# does it basically. C++ does it, starting in C++ 11. Yeah. It's basically the same thing. It's a lambda expression. Yeah? It's an anonymous function that you can use at some point in your program. So let's look at like variable binding a little bit, and of course, like the opposite of a bound variable is a free variable. Yeah. So what are the free variables in this little thing? So I give you a hint with the first one, and then let's do the other ones in the chat. Yeah. So in this expression, lambda x dot xy, x is bound by this input parameter, and y is free. Okay. What's the case for the second line? What is bound and what is free in this function body on the right side? One has a guess? Let's see. No variables free. Yes, x, y, and z are all bound. You're right. I should have waited a little bit longer though. Yeah, no variables free. X, y, and z are all bound. No variables free. Okay, how is it for the last one? Just a hint, it's important where the x is. Y, z are free. No, y and z are bound by the binder on the left side. It's all of these are bound. Okay, the guess is our side x is free. What is our side? You mean the outside? Ah, sorry. It's a typo. It's outside x is free. Yeah, thank you. Great. So outside x is free. That's correct. The first occurrence of x, so the one after the dot, is bound by this parameter, but the second occurrence of x is free. So don't expect the x outside of the parentheses to be bound to the parameter of this function because it's outside. Good. So this is basically how variable binding works. It has a scope. It has the scope of the function body. And if you leave the function body, it is bound again. Yeah. For the second line, for instance, z is bound in the whole function body of this function definition, which includes lambda x, lambda y, x, y, z. This is the whole body of this z function. That function that takes that. And then x is bound in the body of the whole x function, which is lambda y dot x parentheses yz parentheses. And so is y. So in the end effect, like the body of the whole thing is then bound. Oh yeah. Okay, there was again the question about y and z. I hope I just answered that. So the body of z basically is the whole thing, starting from lambda x, lambda y, and then x, y, z. This means that z is already bound here. And then kind of it narrows down. But in the end effect, like all of these variables on the right side are all bound by these bindings on the left. Good. Let's move on a little bit. So combinators. We say that when a term with no free variables, so all the variables are bound, we say that this is a closed term. And if we have a closed term, this is called a combinator. And the most important combinator that you have is the identity function. The identity function is a so-called combinator. Okay. And it takes a variable, in this case x, and it returns that same variable again. So this is the identity function. Rather boring, but theoretically rather interesting as well. There are more combinators, so more closed terms, more things without any unbound variables. And the other one is a so-called constant combinator. And the constant combinator basically returns a constant term c that does not use x. Either way, what you ever input into x, it just returns this constant term c. And now we need to talk a little bit about like what the operational semantics of this is. We now just looked at syntactic things, things where things are bound. We talked a little bit about variable binding. We talked a little bit about the syntax of this stuff. We didn't talk a little bit about the operational semantics. And the calculus is rather so-called pure because we compute just by applying functions. And this is how function application works. So on the left side here, you have in parentheses lambda x is t12, and then you apply this function to something that is called t2. What happens on the right side when you evaluate that? The result is t12 in a way, but you have in these little brackets a so-called substitution. And this substitution reads that x is exchanged by t2. That means that every occurrence of x in t12 is exchanged by whatever is in t2. And this is how function application basically works. It's just a rewrite, if you will. So this whole thing on the right side means that this is the term obtained by replacing all free occurrences of x in T12 by T2. Which then gives us a leeway to define the so-called full beta reduction. Full beta reduction is one of the many ways how you can evaluate the lambda calculus, but I think it's the most, let's say, reasonable way to do it. This is a rather more complex example. So here you have like a function definition of the identity function, so lambda x dot x, yeah? And then you apply this function to this whole complex thing, which is basically again the identity function, and then a function definition lambda z, where the body is the identity function applied to z. Well, so basically a lot of identity functions in a complex way. So we can rewrite this and just say, okay, identity lambda z dot identity z. Basically the same thing. We just rewrote it so we can read it a little bit better. And then how do we start evaluating that? And full beta reduction starts at the leaf term basically. And the leaf term in this definition is here the function definition inside of the function definition, which says id of z. And id of z evaluates to z, which means that the resulting term is id because this doesn't change, and then lambda z dot z. Yeah? And then this is the little underline here, which is the next step. We take the next leaf term. Inside of the function definition we cannot evaluate anymore because z is just a bound variable. We cannot do anything about that. But we can evaluate the next outer thing, which is the id function. This is a function application. We can do that. So id applied to lambda zz will of course result in lambda zz because it's the identity function. It would return the same. Yeah. And then again we have this outer id left, which we can also evaluate now, and then we have lambda zz. And lambda zz is something that we cannot do anything anymore. Yeah. We could say that we're stuck now, but not in the lambda calculus, because the values of the lambda calculus are functions. That means when we have a function that we cannot reduce anymore, we have found our value. This is a little bit weird because we're always thinking like terminal values, like true, false, or 0. Yeah, and in the lambda calculus, it's a little bit different. So functions are our values when we cannot evaluate them anymore. This is a little bit weird to get into, but you will get used to it in the next few sessions. Yeah, so this we cannot evaluate anymore. So we're now at the end of the so-called full beta reduction. There is a so-called normal order to evaluate things. So this is another way to evaluate the lambda calculus in like a different order. And this thing basically starts from the outside. So we look at the outermost term, which is id, yeah, and apply it to the argument, which is id lambda z id z. Yeah, and we result in the inner thing because it's the identity function. Yeah. We can apply the same thing again, and then we go into the function definition and look into the body if we can apply something in there, and we result to the same thing, and we cannot evaluate anymore. So basically you come down to the same thing as full beta reduction, but you don't start from the inner, you start from the outside. So that's called normal order. Another way of evaluating the lambda calculus, because we didn't have enough ways already, is so-called called by name. So same thing again. We also start from the outside. Same as lambda z is the identity function. But what do we gain if we exchange this by id again? It's just to illustrate here. I didn't want to use a more complex example. So lambda z is also the identity function, but let's not change that a little bit here. Yeah. So call by name, as you can see, also works from the outside, but then we are at this point where in normal order we would evaluate inside of a function body. We don't do this here in call by name. This is our end result. So whenever we have, like on the outermost term, a function definition, we're done in call by name, and evaluation stops at this particular point. Oh. Why are people doing it this way? This is just a way how to implement your interpreter, basically, and what you want to have your end result to be. If you want to go inside of the function, you have gotta have full beta reduction in normal order. Call by value is basically the same thing. So you start with the innermost term that is not a function definition. So the innermost application, and the innermost application is this underlined part here, which of course evaluates to this, which of course evaluates to this, and there you get, there you stop again, because you don't evaluate anymore. So the call by things, don't just evaluate applications and don't go into function bodies to evaluate. So this is the only distinction to make. Usually when we evaluate the lambda calculus, we use full beta reduction, but be aware that there are other ways to evaluate the lambda calculus as well, depending on what you want to have. No? Good. One question that we had open is how to deal with multiple arguments. So the lambda function only takes one argument. We can achieve multiple arguments by so-called higher order functions. So let's say we have multiple arguments. This would like this first line here. So f lambda xy dot s. So x and y are the input parameters and s is the body. We can rewrite this as lambda x dot lambda y dot s, and when you apply these functions, you can use these multiple parameters just in a row. So fvw would be f applied to v, so the x, which then again results in a function starting with lambda y, which is then applied to w, and then gives you the body of S where x is exchanged by v and y is exchanged by w. So we can simulate multiple arguments, but just chaining lambda expressions, lambda functions in a way, lambda abstractions. And this is called currying. This is called after a man called Haskell Curry. That's him, another American mathematician and logician, and he is known for so-called combinatory logic, and he's also known for the Curry-Howard correspondence, which we will learn in one of the next lectures. And if you happen to know the Haskell programming language, this is named after him. This is an honor to Haskell Curry. Good. And coming back to the other logician that we had, this Alonzo Church that invented the lambda calculus, we can do all sorts of crazy things in the lambda calculus to simulate program behavior. For instance, these are called Church Booleans. So Church Booleans are basically lambda definitions taking like two arguments, so like chained two arguments, true and false, and this thing, the true thing, just gives us back the first thing, and false gives us back the second thing. And by this little neat trick, you can actually express Boolean operations in the lambda calculus. It will get much clearer if we use them. So this only evaluates to t and only evaluates to f, and basically throws away the other argument. So we can define a function called test, which just takes L, M, and N and applies L to M and the result of that to N. So this is a function we call test, just semantically. Yeah. And this is the Boolean to check. So the first argument is kind of the if you want to check if it's true or not. Yeah. And the second and the third argument are basically the path in an if that you would take if either it was true or false. Yeah? And then you could just see from the structure that this is basically the same thing as an if. So let's say test true VW. Yeah, let's reduce that a little bit down. This equals to this very long function applied to true v and w. And the first thing that you do in function application is you consume all these arguments and you produce the substitution. No? And this is what happens there. So true you just exchange by L you just exchange by true, and then M you exchange by V, and N you exchange by W. So the resulting operation would be true VN. So this is the thing that you do. So then let's exchange true by its function definition. So this is equal to lambda t lambda f dot t applied to V and W. So again, we do the same thing. We exchange variables. So t is then exchanged by v, and f is exchanged by w, but f is not in the body. So the result is v. So you basically have used true to evaluate an if there. And this is how like conditionals play out in the Lambda calculus. Like from the very basic working of things, you would have not imagined that we already had an if in the language, but we do. We can just do this by selecting arguments. We can also find like conjunctions. So this is an and in Boolean, in church Booleans. So lambda b, lambda c is b, c, and false. So this looks like we're building something useful. We can already like throw away our little B language and exchange it by the Lambda calculus and be in the same thing. Have the same power. You can also do this for an OR, for an XOR, for an NOR, and whatever you feel like. It's just a way of like combining arguments with true and false here. You can do data structures. You can do things like pairs. So this is a lambda pair. This is basically a function that takes f, s, and b and applies b to f and then the result to s. And then selecting the first argument is basically taking such a pair and applying it to true. And the second you get by applying p to false. And then you can combine things together in pairs. You can also do numerals. We can also throw away our n language and build the same thing using the Lambda calculus. So this is the church 0, which basically takes two arguments, s, which is standing for successor basically, and 0 at z, which is basically the 0 value, and then you return z. So this is a church 0, successor 0, 0. Seen this before. Maybe that's a hint to look at the previous slides to see if you find 0 again. So a function that takes two arguments and produces the second one, that's false. So you just name it differently, but like essentially it's the same structure as false. And as you can see, like you can build all sorts of relations between these little neat things by just having the same structural properties. Good. So C1, so the representation of a 1 is then the successor function applied to 0. You already know that from the other language. C1 is the successor applied to the successor of 0, and C3 is then the successor of the successor of the successor of 0. So this is basically the same thing as in our n language. Can we calculate with those? Yes, we can. We can also define operations. We can do a plus. We can do a times. So a plus is basically a function of 4 parameters, m, n, s, and z. Yeah? And then you apply m to s, to the successor of the operation of n to the successor of 0. And if you insert m and n, so the parameters basically, church numerals at this point, you will come to a church numeral that is the addition of m and s. M and n, sorry. Yeah. And you can reuse plus then to do a times. Yeah. So m applied to plus n applied to C0 is basically a multiplication of m and n. Yeah. It's rather complex. It's rather slow, as you can see, but you can do the same thing as any other programming language here. Yeah, first numeral, second numeral, and so on. Now we come to the thing that I hinted to a little bit before when it comes to termination. In the Lambda calculus, we can formulate functions that do not ever terminate. Yeah? And we call that divergent term. No? And we call a term which cannot take any step under evaluation a so-called a term in normal form. And when we now look at this combinator, it's the so-called omega combinator. So a function definition, lambda x, where x is applied to x, and then this function definition is applied to another function definition called lambda x dot xx. What you do if you evaluate this once, if you evaluate this function application, is you come to the same thing as before. So the term that you evaluate this to is the same as before. And this is why we call this a divergent combinator, but because by reducing it, you get the original term back. Yeah? And terms without such a normal form are called divergent. They diverge. That's kind of the vocabulary that we use here. Yeah? So why is this useful? Why would we do such a thing? Why would we build such infinite loops into our programming language in the first place? Because we can use it to define recursion. And don't worry if you do not get this at the first instance that I explained it to you. We will have it at some point. But this is how you do recursion in the Lambda calculus. Yeah? This is basically the omega operator, the omega combinator, in a little bit more complex form. And we call this the so-called fixed point combinator, or the so-called Y combinator. You might have heard this a little bit before. There's a very famous website called Y Combinator as well. This is where it comes from. And we call this function fixed because it's kind of the fixed point combinator. And what it does, it takes an argument called f. And in the function body of that is a more complex use of the omega function that we've seen before. So this is basically the omega combinator that we've seen before. But as you can see, it takes lambda x and applies f to a function definition called a lambda y dot x applied to x applied to y, and the right side is on the right side. And this is a combinator which we will be inspecting a little bit more closely in the exercise, because it helps us to define recursive problems in the Lambda calculus. We couldn't do this before without this combinator, but now we can do this. Yeah? And this helps us to define recursive definitions of mathematical problems inside of the Lambda calculus. Be sure, we will repeat this a little bit. Don't worry if you didn't get this in the first instance, but try applying it in the exercise, and then you see the mechanics of these things. Also stop yourself, because it's recursive, yeah, and because it's divergent, you do not want to over exceed yourself in doing this manually. No? Let's do a little bit of an example. Yeah. So you have this fixed combinator. This is the same thing as in the previous slide. Yeah. And you have a function that we just call real equality, and it just checks for the equality of two arguments called m and n. No? And this is basically a function called equal that we do not define here, that checks like this true this equality of m and n, and if this is true, it returns true, and if it's false, it returns false. No? So this is basically like a test function in a way. No? And then we use this generator function. This is this g here. By the way, when we write equals, this is just syntactic sugar. We can just replace this back and forth as we like. It's just syntax substitution. Yeah? So we have this generator function called g, which takes an argument that we just call fct, just to see. Yeah, this is a 3-letter variable, but it's still a variable. And in the body of this function, it is another function definition called lambda n. And then there is like of a little bit of a mix. Think you have ifs in this way. It's just a little bit more complex to write this in lambda calculus, so I've shortened it a little bit in terms that we all know. Yeah? And then we say, okay, if real equality of n and c0, so if n is 0 basically, then we return c1, else we return the times of n applied to fct factorial of the product of n. No? So this is the generator function. And then we take the fix function up there and apply fix to the generator function. No? And what we did there is pretty much interesting. So we now use the fix combinator in its general form with a generator function, yeah, to describe a mathematical problem. And the way this is terminates is actually with this if real eq n c0 then c1. Yeah, this is why we don't reproduce ourselves anymore at some point. Yeah. This will actually be part of the exercise, and if this troubles you a little bit in the exercise, I will present it here in the next lecture a little bit more. But this is something that you really need to try out for yourself. This is not something that I can explain very properly on slides. You gotta have to do this at least once yourself. With just a tip, very, very low values. Yeah, try with very low values, otherwise you will get lost on your paper. Good. A few definitions we already need. How do things work in the lambda calculus actually? So one of the things is called the countable set of variable names, and this is this set called V. Yeah. We need this definition later on for proofs and for other definitions. Yeah? And let's say we have V as the countable set of variable names. Then the set of terms is the smallest set of T, smallest set T, such that these three conditions are met. So x is in T for every x in V. So variables are terms in the lambda calculus. So this is just a different definition than the definition we've had before for the syntax of the lambda calculus. Or the second case, if the term T1 is already in T and the variable x is in V, then we can also say that a function definition, lambda x dot T1, is also in T. And if T1 is in T and T2 is in T, then the application of T1 to T2 is also in T. So this is the inductive definition, basically, of the syntax of the lambda calculus. Yeah? this is sometimes helpful for proofs. That's why I give this definition. Yeah. You can also, of course, just for intuitiveness, I always give this little instance that we've seen before. This is the format that I use. But for proofs, sometimes you may need this. Yeah. Especially if you want to use it in other definitions as well, like this. So free variables. What is a free variable? A free variable is an unbound variable. The set of free variables of a term t is written as fv of t and is defined as follows. So free variables of a variable called x is just x. Yeah. And if you look at function definitions, the free variables of a function definitions is the free variables inside of the function body without x. So x is not a free variable anymore when it has been bound in the function. No? And for function application, that's basically free variables of the function unified with the free variables of the parameter that you take. This is just free variables. Sorry to throw a few definitions at you at this point, but you will need them at a later point. It's important that we just go over this and understand what we talk about when we say free variables. Substitution I already teased on a little bit. So substitution in the Lambda calculus is the way how to apply functions to parameters, like functions to parameters. Yeah? And we have to look at how to do this correctly. So we will try it a little bit out, and I will tell you a little bit what the problematic parts in the substitution are and what we need to think about when we come to variables and scoping in this. So this can be a little bit tricky. Yeah. So let's do a first definition for substitution. Yeah. So let's say we have this substitution on the left that says, okay, for every occurrence of x in x, exchange this with s. So that means like the result is s. Yeah? And the other thing is like the second line reads, so substitute x for s in every occurrence in y. Y is also a variable. And this is equals to y only if x is not equal to y. Because otherwise you would exchange that. Otherwise you would have the first case. So how does substitution now work for function definition and function application? So when you have substitute x by s in this function definition lambda y t1, then you just push the substitution inside of the function body so that the new resulting term is lambda y dot, yeah, and then exchange x by s in t1. And then you can reapply and reapply and reapply until you're at that point where you cannot do it anymore. Yeah? For application, that's basically the same. You push it inside of the applications. Yeah? So this is formally a function, yeah, by induction over its argument t. Yeah? Just to give you a formal notion of this thing. Okay, how does this now work in practice? Let's try it out. Yeah, let's try out what it works. So this is the rule set that we just think. This is nothing new. This is just the thing that I just presented to you. Let's try this out. Okay, let's try exchange x by lambda z dot zw. Yeah, inside of this function definition lambda y dot x. How does this work? Well, the result is lambda y dot lambda z dot zw because we just exchanged x by the thing that we had in there. Okay, this seems to be working very good. Let's go on. Now you have the identity function. So this is exchange x to y in the identity function. And the result of our rule that we had before, because we just push it inside of the function body, would be lambda x dot y. This is weird because the identity function after our substitution is not the identity function anymore. This is not something that we want. So we might have a problem at that definition. So let's change it up a bit. Yeah? And the problem is we did not distinguish free from bound occurrences of variables. We just exchanged stuff. So let's do a little bit of a different thing. So this is the same definition as before, but just the third line is exchanged, and we have now a case distinction that says, okay, if x is equal to y, so the thing that we're substituting is equal to y, then let's not substitute, and in any other case, let's substitute. So this would help us in the case that we just saw. So let's try this out again. So let's take this example, which says, okay, exchange x by z, in lambda z.x. So this is kind of a constant combinator before, and now it becomes the identity. Okay, this is also weird. We don't want that to happen. And this is an effect we call variable capture. This is also not something that we want to have. So how do we do this? Well, we alter the third rule a little bit and avoid now variable capture. And this means that we have now a new argument in the second case of the third line saying that if y is not x and y is not in the free variables of x. So that means that y can never be captured in this way, because we can't check for the free values of s, and so it won't ever capture this. Let's try this out again. So we have now this example. So saying like exchange x to yz in lambda y dot xy. Okay, how does this work? This also wouldn't work because now we cannot exchange anything because y is in the free variables of s, and we wouldn't exchange anything here, and we can like apply it to that. So this might be a little bit too conservative. And to actually help with that, we need a new definition called interchangeable terms. And the definition for that is that terms that differ only in the names of bound variables are interchangeable in all contexts. That's meaning the name of any lambda bound variable can be exchanged by any other name at any point where this is convenient. This is rather helpful. That means that we can exchange names all of the time if we happen to want that. And this means we can formulate our substitution a little bit like this, and leave out the first case because we don't do anything there anyway, and say if y is not x and y is not in the free variables of s, we can do that. And then if we have the case that y would be there, we can just substitute names. We can just exchange names, and then we won't have this capturing problem anymore. Okay. So this is the final definition for substitution. This is the textbook definition for substitution in the lambda calculus that we want to have. So if you want to remember one, this is the one definition to remember. The other ones were just helpers that helped us get to this point. So don't worry if you didn't get the other ones. These were just stepstones to see, like to produce a valid definition for substitution in that sense. Okay. Good. So in summary, the untyped lambda calculus looks like this. So the terms in the untyped lambda calculus are just x as a variable, the function definition lambda x dot t, and then the application of a function, so t applied to t. And values in the lambda calculus in our definition syntactically are just functions. So anytime we have a function, we're good. This is fine. Abstraction. We call these abstraction values, by the way, because we call a function definition an abstraction in the lambda calculus. and these is then an abstraction value. Evaluation then works like this. It's only 3 rules. Yeah, this is very, very nicely done. And we didn't have these before, so let me introduce them. So the first application rule, the EAP1 rule, basically tells us if a function that you apply to another value, another function, if it can be evaluated, please evaluate it. Yeah. So the first thing that you always do on a function application is you evaluate the left side down to something that cannot be evaluated anymore, a value. And if this is the case, then it has the form that is matching the EAP2 rule. That is, in the conclusion you see v1 for value 1 applied to t2 is v1 applied to t2 prime. And this means that you can evaluate the value also down. So the first thing that you do in an application is you evaluate down to a value the function that you want to apply, and then you do the same thing for the argument. And if you have that, then you have the right correct form for the third rule, which is the e-application abstraction rule, the EAP-APS rule. And there you see you have the following form. On the left side of the application, you have lambda x.t12. This means you have a value, which is just a function. And you have an argument, which is also just a value. And the rewriting that is going to happen is that you substitute now x, so the parameter of this function, by v2, the parameter that you put in, the concrete parameter, inside of t12, and then you apply the substitution that we just carefully defined previously. And this is the untyped lambda calculus. This is all it. This is all you need for Turing complete computation. Rather complex. It is rather simple, but it's rather cumbersome to actually compute with that. We're going to try a little bit, but sooner or later we have some convenience functions to work with that. This is all based on chapter 5 of the book if you want to read it up. And in the next lecture for next week, we're going to talk about how to type that. Currently, we're talking about how syntax and semantics of the lambda calculus works and what you can basically do with it. I've shown you that we can do the same thing as the languages that we defined in the last lecture. So it's at least idempotent. Maybe it can do a little bit more. And I've shown you like bits and pieces of like recursion that we might do with that and calculation that we can do with that, things like that. But in essence, it boils down to these 3 evaluation rules. Okay, content-wise, that would be it for today. I'm happy to take questions as long as you got them, and then upload everything that you need for this week. So if you have more questions towards the lambda calculus, just let If not, this is also fine. Again, you can do this in Panda. If you rewatch this, you have this. Oh, we have an organizational question. This is also fine. Let's see what it is. Maybe we put it to the Panda forum so that everybody, not only the people in the chat, know. But let's hear it. If I could do a 15-minute break in the middle of the lecture. Yes, of course I can. But you can pause the lecture at any time. You just won't be live. But I can do a live break of 15 minutes in the middle if you like. If everyone agrees, we can do that. Maybe I'll put a vote up for that in Panda so we can see how the majority of the course feels about that. Is that a good idea? Okay, so I will do a vote on that and let's see how this comes out. First lab is released. Let me just check so I can give you the live numbers. Oops. So first lab is released today at 12 o'clock server time. That could be already out there. You should see like lab 1. And the due date, the deadline is April 29th, so that's 2 weeks later at 8 a.m. No? So that's the first lab you see there. It takes you through. It's basically the topic is evaluation for the B and N language that we had in the last lecture. And the second lab is then regarded for type checking for this N language that we had before. And that will be released a week after on April 29th, and is then the deadline for that is then 2 weeks, and then it will be just a 2-week regular interval for all the other labs then. Good. So I just checked the stream logs, and sometimes there were a little bit of outages, maybe because of the connection. But I'm doing the recording on my computer, so the thing I will upload to the university servers will then be complete. In case you missed a word or two from me, these will then be complete. Good. With this, I'll leave you for today. Remember, there is the first exercise sheet is already up there. The first lab should be available to you sometime today. So be sure to do both of them. I am still figuring out a very cool way to do the exercise sessions. If you have suggestions for that, please let me know. I'm happy to take suggestions there. Just post them into the Panda forum. That would be very nice of you. Also, you've seen that like the start of the stream always has a nice music to start you into the day. If you have suggestions that are like either Creative Commons or free licensed, just post them also to Panda. I'm happy to include also your suggestions there. Doesn't need to be just the music that I found. If you have suggestions, please let me know. And if you have trouble with the exercises or the labs, also let me know on Panda. That would be pretty neat. Good. With this, I wish you a happy rest of the day, and I'll see you again next week at 10 a.m. Thank you very much.